Hello again, everybody, and welcome back. We're going to be moving towards the end of our Chapter 10 notes, and so far we've been talking about things like momentum, that is the product of mass times velocity, and the momentum is always conserved in any kind of collision. And we talked also about a type of collision called inelastic collisions. That's where some energy is lost, like when two cars crash into each other and crumple up. Some of the initial energy that each car had is lost into that crumpling process. Well, the last part we're going to be talking about is called elastic collisions. And if you recall from inelastic collisions, the difference with inelastic collisions and elastic collisions is that, well, first of all, in any collision, momentum is still conserved. The total system momentum beforehand is equal to the total system momentum afterwards, all right, initial and final. But the difference is this right here. With elastic collisions, the assumption is you have two objects that are, ideally, we would say, perfectly elastic. Now, in the real world, there's no absolutely perfectly elastic object, unless you're talking about certain subatomic particles, but very elastic objects are things like, well, if you've ever seen those Newton's Cradle things where there's like 5 or 6 balls hanging from pendulums right here, and you pull this one back and then it swings down and this one comes out. These spheres right here are made of very hard, well, they're just made of metal, but they're metal such that it doesn't compress very much. If the energy from one is transferred to the other one, the energy is transferred right through with very little loss of energy. So we can say they're essentially elastic objects. And so what that means is, since it's elastic and no energy is lost, then we can say essentially the initial kinetic energy before a collision of the whole system is going to be equal to the final kinetic energy of the system. This is the difference between elastic collisions and inelastic collisions. And so both of these assumptions have to be true in the equations that we use. Momentum is conserved and energy is conserved. All right, both of these have to be true. So one way we can think of this is actually to look at it in terms of that Newton's Cradle thing. All right, that's the thing that I just kind of demonstrated to you right there. The metal spheres that kind of click back and forth because they're very elastic and transfer energy very well, with very little loss of energy. So here's kind of a thought experiment right here. All right, I'm going to take this and move that up like that. All right, hopefully you can still read it. So let me just go ahead and draw one of these right here. It's not really a calculation, but it is something to think about. So, well, let's just go ahead and read it first. I'll make this a little bit bigger here. All right, so the Newton's Cradle, we've all seen these before. It's a tabletop toy. If you drop one ball on one side, okay, one pops out on the other side, all right, and then it clicks back and forth, right? If you drop 2 on one side, if you pull 2 back and let it hit the rest of them, then 2 pop out on the other side, all right, and then 2 swing back and forth. All right, so let's see if we can just sort of sketch this right here. Right there, okay, 1, 1, 1, 1, and you pull 1 back from the top right here, then 1 pops out, etc. If you pull 2 back, straight down, straight down, straight down, then 2 will pop out on the other side. So if you've ever played with one of those, that's how it works. All right, you have certain masses with certain velocity hitting right here, and so it causes the same mass with the same velocity to shoot out on the other side. All right, that's conservation of momentum. All right, and so your friend looks at this and says, all right, the way it's worded right here is a little funny, but we'll just read it. The conservation of momentum wouldn't be violated if I dropped 2 balls on one side and then only 1 popped out on the other side with twice the speed. You hear what he's saying? So it's saying this. So the conservation of momentum says that the mass times the velocity before and after collision have to be the same. So he says, why couldn't this happen? Why couldn't you have 2 of these right here swinging and hitting all the rest of these, and then having, so it's a certain mass Oh, actually, I'll say two masses, right? There's two masses. So you pull two of these masses out. Two masses times velocity. Why couldn't you have then one mass pop out on the other side with twice the velocity? So that's like flying up twice as high as these right here. Why does it always happen like this? Two masses with a certain velocity and then two masses with the same velocity. Why couldn't you just have one mass, which is really half of that right there, right? One mass with twice the velocity. Isn't that the same thing? 2 times mv and then 2 times mv. So that's what he's saying right there. What we said, why does that not happen? Explain to your friend why this does not occur. All right? So why can't we have that? Let's see if I can shrink this down. Oh, no, that's going to be going with it. Oh, that's all right. Well, your friend is pointing out that momentum has to be conserved, and this is absolutely true. Momentum is conserved right here. Okay? Oops, well, momentum is conserved. But what else is conserved? Energy is conserved. Conservation of energy. And so, on this side, with the two spheres hitting, we have a certain kinetic energy. Kinetic energy initial is going to be 1/2 times, what's the mass? Well, kinetic energy is 1/2 mv squared, right? So 1/2, 2 times whatever the mass of one of those spheres is, times the velocity squared, right? That's the initial kinetic energy happening right here. What's the kinetic energy of this single mass with twice the velocity? Kinetic energy final equals 1/2. What's the mass? Just m, right? Just one mass. Times, what's the velocity? 2v squared. All right, it seems like everything is the same right here. But what is the difference? Why can this not happen? The answer is because these are not equal to each other. They're equal with conservation of momentum, right? Because 2mv equals 2mv. But what's different down here? The fact that you have 2m, but then over here, you're doubling the velocity, and that velocity is squared. So really, this 2 gets squared as well. So you're going to have 4 times, well, actually, twice, 2 times this energy coming out as you would have going in. So that's why it's not equal. All right, the velocity is squared, and so if you double the velocity, that double gets squared as well, and so that changes the whole equation. That's why this is not true, and that's why that doesn't happen when your friend says, okay, well, conservation of momentum says this should be able to happen right here. That's true, but with conservation of energy, and this is what happens with elastic collisions, the initial energy has to equal the final energy. If you have the mass but double the velocity, that can't happen because of that whole square action going on with the velocity right there. So that's our example 10.9. Hopefully that made sense to you. So the problems that we're going forward with, we're going to have 2 constraints. One is that conservation of momentum has to be in place, and conservation of energy has to be true as well. That's going to be our guiding factors for the equations that we make up. So there's an example 10.9, a thought experiment, and thank you for watching. I'm going to see you on the next one.